Welcome to the Rambus Design Summit 2023. It's a real pleasure to be here. Big thanks to Mark for giving the audience a great overview of how CXL addresses some of the challenges that we're seeing in the data center. With my presentation, I'm going to be giving you a brief technical overview, especially some of the new novel device types and capabilities and interconnects that have been added in the CXL 3.0 specification itself. And some of those primary features that have also been enabled. My name is Danny Moore. I've been working in the interconnect space for some 20 years, primarily focused on PCIe switching and fabrics. And really in the last 4 years, I've started to get really engaged in the CXL specification and CXL consortium. I'm currently driving CXL product management at Rambus, and I get to speak to you today specifically on some of those new device types and capabilities that I mentioned previously that are being introduced in CXL 3.0. So for the agenda today, we will give you a quick overview of the CXL 3.0 specification itself. Then we jump into some of the new device types, the multi-headed device in particular that have been defined in CXL 3.0, as well as some new capabilities, which we call the dynamic capacity device capability, which really gives some additional composability to the memory subsystem, and then some of the new interconnects that we have in CXL 3.0 and their fabric capabilities that have been added. So let's jump right into the 3.0 overview. So with the 3.0 specification release, we get a ton of great new capabilities and features. Now there's a lot of overlap on these features, with CXL 3.0 really bringing composability and compute disaggregation to the next level. The fabric capabilities that are added and the management's been expanded. And, with that, we define a new port-based routing elements in the 3.0 fabric switch. So we're no longer confined by those host-defined domains that we see in contemporary PCIe type hierarchies. We've improved memory sharing and memory pooling. The pooling functionality itself has been expanded with the new device types and capabilities, which I quickly mentioned and will be introducing today. And the memory sharing itself has been defined altogether. So now resources in separate domains can now share the same underlying media capacity, supported by spec-defined hardware coherency mechanisms that previously didn't exist. So now, memory can be simultaneously accessed by more than one host and still guarantee the same host sees the most up-to-date data at that location without the need for the host itself through some sort of software managed mechanism to coordinate that effort. And some of that touches on what we call the symmetric coherency concept highlighted here. With 3.0, we really move away from the previously CXL bias-based coherency mechanisms. So now devices themselves are actually able to invalidate a host cache. And really, it's this key feature that enables a whole litany of 3.0 features, including memory sharing, peer-to-peer memory access, and even new topics such as near memory processing. And of course, all of this is done while maintaining the same backward compatibility that we're used to seeing in the PCIe space. So here I show a chronological representation of the CXL features as they're pinned to their prospective specification release. We see a doubling of the transfer rates as we move to CXL 3.0, as we're now sitting on PCIe Gen 6 electricals, as opposed to previously sitting on PCIe Gen 5 electricals with CXL 2.0. And in terms of raw bandwidth, this will give us 256 gigabytes of bandwidth for a by 16 link width. Now, obviously, flip packing, link overhead extracts from this raw bandwidth. So actual throughput will really be based on a particular workload. But the underlying support for an extremely high bandwidth link is there with PCIe Gen 6. And then, of course, we gain a lot of the benefits of PCIe Gen 6 FEC and CRC. So we get those same strong, reliable, error-free link operations that we're used to seeing on our PCIe interfaces. And then the additional space within the expanded 256 byte FLIT, which you can see highlighted here, allows us to get some higher throughput. And that FLIT itself also is really the building block that enables much of the 3.0 feature set, including the fabric capabilities, the sharing, this symmetry, and the peer-to-peer items that I had mentioned previously. So let's hop right into some of these new device types, in particular the multi-headed device definition. So pooling itself is not new to CXL 3.0. You know, with CXL 2.0 really bringing the pooling concept to fruition with switches and MLDs, or multi-logical devices. But with the MHD, bringing some new optimizations in CXL 3.0. So in 2.0, single logical devices or multi-logical device-based pooling was really enabled via switches only. And they were resources that could be dynamically defined to hosts, but you always had a requirement to have a switch in order to fan out multiple endpoints to a particular host. Now, in 3.0, we introduced this multi-headed device capability, which really eliminates the need to have a physical switch to implement the pooled memory solutions that we're also interested in. And obviously, we can expect some performance benefits as well. You know, in particular, around latency, as the FLITs are no longer needed to traverse a CXL switch, and in combination with some of the capabilities that I discussed later, we get some great improvements on the device composability as well. So with the MHD concept, we can now build pooled-based memory solutions without switches at all. So let's double click on the MHD types themselves. So there's really two types of MHDs defined in CXL 3.0. There's the multi-headed single logical device, or MHSLD. There's the multi-headed multiple logical device, or MHMLD. MHSLDs and MLDs are really just differentiated on how the resources of the underlying media attached to the controller are presented to each of the hosts. So the MHSLD presents an SLD to each head. So we have a one-to-one mapping of logical devices to heads, and each head attaches to different hosts. The MHMLD presents an MLD to each head. And so what that means is that we can actually attach multiple logical devices to each head, you know, up to 16 logical devices being mapped to a single head. Now, really, to enable this MHMLD functionality, we do need switches, just like we did in 2.0. But now with the MHSLD, you know, composability on the memory subsystem, CXL attached memory subsystem is fully implementable without CXL switches. So the functionality between the two is very, very similar. MHMLD does provide some additional flexibility, but we can see both devices here presenting a logical device abstraction layer. And really, it was implemented this way so that we could maintain the existing logical device management framework that was previously defined for MLDs in 2.0. So with that, we have both some forward-looking flexibility as well as backward compatibility between the management framework that was implemented. So now let's dig into some new capabilities that have been added, and in particular the DCD capability framework, which, as I mentioned before, is going to bring some additional composability into the memory subsystem. So really, what is the problem that DCD is trying to address? Prior to the definition of DCD, allocating and deallocating memory is very disruptive. Capacity is needed to be added and released by reprogramming the HDM decoders themselves. And really, for that to take place, the host traffic needs to be paused or stopped. And often a system reset is actually going to be needed in order to, move some capacity that was previously allocated to host 1 over to host 0. What we'd like to do is address this problem, and how that is addressed is with the DCD framework, which I'll review now. So in this framework, you can see the diagram on the right. There's a slight change. Here the HDM decoders are programmed with the maximum capacity that the device could potentially expose. So here the HDM decoder exposes the entire range of media attached to the controller itself. So in this manner, both hosts at boot up map the entire ranges into their system memory address space, and such that the entire underlying media attached to the CXL controller can be addressed. But this does present a new problem, right? And that new problem is that how do we manage what hosts are talking to what media? If the entire ranges of the media has been exposed to both hosts, how do we restrict what hosts are accessing what media? And that is really achieved through something that we call the extent list. So the Fabric Manager in 3.0 has been expanded to include this DCD management command set, which is used to query and configure the DCD itself. A DCD is simply a device that implements this DCD management command set outlined in the 3.0 specification. So the device's physical media is subdivided into regions, each region being configured by the FM for capacity and the granularity that region can be further subdivided and allocated and deallocated. So the allocation and deallocation of these blocks is maintained in the extent list, which is also programmed by the FM and organized by the system orchestrator. So here the FM is capable of entirely managing which resources are applied to which host and which host can access which resources. Now, a rogue host in this scenario, attempting to access a range that is outside of its approved extent list, will actually be treated as an HDM decoder miss within the CXL controller itself. And so the HDM decoder framework is something that has long existed since early versions of the CXL specification, and that is all fully functional. And so in that regard, that HDM decoder miss is handled the same way any other HDM decoder miss would be handled, and thereby restricting a host attempting to access a range that it hasn't been approved or previously allocated for. So with that, we can see the DCD capability really bringing a fully composable framework where now hosts are no longer required to reset. Hosts are no longer required to remap system memory, as the entire underlying media has been mapped into the system memory already at boot. And now we can simply allocate and deallocate, update extent lists in the hosts, and then have the new host accessing new memory ranges. So with that, let me proceed on to the interconnect aspect of this presentation and start talking about some of the Fabric capabilities that we have brought to fruition in the CXL 3.0 specification. So with 3.0, we're no longer restricted to the familiar tree-based hierarchies that we find so pervasive in the data center, where resources are really confined to host domains only. Right. In CXL 2.0, the switches were able to provide device fan out, expand the size of any host's physical address range, but communications were restricted to only within that domain. And with 3.0, we are really now starting to enable these cross-domain communications, which you can see highlighted in the diagram on the left. And with this, CXL 3.0 defines a new type of switch, and that is a fabric switch. And the fabric switch uses a port-based routing mechanism to really bring these capabilities to life. And then in the addition to that, we've also defined some new fabric manager capabilities for fabric attached memory devices. So now we've built a new framework around port-based routing, switches dedicated to port-based routing, we call them PBR switches, and then new device types, which are really fabric device types, which also understand and are capable of creating flits using source and destination IDs in the port-based routing mechanism. So here are some examples showing the level of flexibility that have been architected in the CXL 3.0 specification, showing both PBR, port-based routing switches, as well as HBR, or what we consider a 2.0 type switch, a host-based routing switch. We can also see that the PBRs can be implemented using mesh type topologies. So you no longer are restricted to a single path between switches. You can have multiple paths between switches. So it allows you to design the bandwidth as you see fit. Now, such topologies, mesh type topologies, can create the potential of deadlock due to their circular dependencies. But this can really be avoided with careful attention being paid to the routing cables within the PBR switches themselves, which once again, we have a management framework defined in the CXL spec for the fabric manager to manage. So, how you define to create those tables is really implementation dependent and really outside the specification. But what we try to do within the specification itself is to make sure that the framework is there so that any management capabilities that are needed are present. Now, the representation of the diagrams here isn't to show a limitation of what type of hierarchies can be implemented, but rather to express, the flexibility and the lack of limitation that has been attempted to be implemented in the 3.0 specification, just really to enable a large litany of potential networking fabric topologies. So the new fabric features really provide a robust path to expand composable systems even beyond the rack. As you can see, the new port-based routing mechanisms allow us to connect swaths of switches, HBR, PBR type switches, and many devices. And all of this fabric also expands the load store interface, which, historically we were confined to the load store interface being directly attached to the CPU. Now with CXL, the load store interface expanding out even to a fabric of switches. And really a lot of this is enabled with the port-based routing IDs that are implemented, and as part of the CXL 3.0 256 byte flit. And it's really these port-based routing IDs that are going to allow these interswitch links to carry traffic from multiple VHs or virtual hierarchies without any sort of address collisions. Each virtual hierarchy kind of having its own address domain. How do we get between the two virtual hierarchies? So we extract out the address domain altogether for the interswitch links, and we focus on port-based routing. And that is enabled in the flit with a 12-bit source port and destination port IDs. And so with those dedicated 12 bits, we can see that, we start to enable really beyond the rack infrastructure. We can have up to over 4,000 sources over 4,000 destinations. And so we can start to conceive of, composable systems that are really beyond the rack. And with some of these fabric definitions that we've performed in 3.0, we've also expanded the definition of some new fabric attached devices, such as the GFAM device, which is a global fabric attached memory. So the GFAM device comprehends these source and destination IDs. It can also generate flits using source and destination IDs. And so, hypothetically, we can start talking about systems that are 2,000 hosts, addressing over 2,000 GFAM devices, kind of creating that large composable infrastructure that I was talking about previously. So thanks for your time. It was great presenting. We do have a Rambus CXL memory initiative. If you're looking for some more information, you can head over to rambus.com and access some of our resources there. We've got lots of training material, white papers, blogs, webinars, etc. I hope you enjoyed my presentation, and thanks so much for your time.